Okay, today we're still here, matrices and arrays. You're gonna see a lot of things been repeated. We will learn, as we already know, creating matrices, but maybe we'll learn a little bit more how to do subscripts, how to call a certain column in the matrix. Transpose, we already know, but we're gonna just go through it fast. We're gonna learn a little bit about elementary matrices. There's some special matrices that MATLAB provide. We're gonna see those, make sure to play with it. Then we'll talk about arrays, element by element operations. Again, we touched a little bit on those previously, but it's good to touch on it since we are in the matrix chapter. The objectives for this chapter would be you'll be introduced to the ways of creating and manipulating matrices in all possible ways. We will introduce you to matrix operations, character strings, the uses for matrices in population dynamics. I don't promise you to go in the Markovian process. It's too much detailed into industrial engineering, so I would assume that you guys go through it on your own. I wouldn't ask you about it in the exam. Then we will talk about how to solve system linear equations, the matrix method of mathematics to solve linear equations, and implementing that in MATLAB, which is important to you. And I don't think we're going to cover the sparse matrix, but it's there in the textbook if you want to go through it. Okay, we will start with an example. We have a concrete example in your textbook. So there is a ready-mix concrete company having 3 factories, as you see in the table. Factories S1, S2, and S3. They should supply to 3 building sites, which is D1, D2, and D3. The cost in whatever currency you decide of transporting a load of concrete from any factory to any site are given by the cost table that we have here. Now the factories can supply 4, 12, and 8 loads per day, respectively, and the sites require 10, 9, and 5 loads per day. Now the problem is to find the cheapest way to satisfy the demand at the site, and we assume that the factory manager proposes the following transportation scheme as we see here as S1, S2, and S3, and for D1, D2, and D3. Now we're going to represent those in matrix style. So we're going to have matrix, and we call it C, and we have another matrix, and we call it X. Remember those tables. So C will represent the first table, X will represent the second table. Now we will say the total would be the multiplication of C and X. Again, there is factories and how many loads for each factory, and there is a cost per load. So if you multiply these together, you're going to get the total cost. That's what we're doing here. Total would be C multiplied by each component in matrix X. You can realize the dot over here. Then we would say, what is the sum of the total? And if we do the total, we're going to get back those values. If you do the sum of the total, you're going to get 114, 138, and 120. That's for, remember from the table, that's for D1, D2, and D3. Now, if you want the total cost, would be the sum of the total, and that would be 372. If you want to go ahead and do it in your MATLAB, please do so. I'm going to switch to my MATLAB. So you got in your tables, C equals 3 space 12 space 10, then semicolon. Now you're creating a matrix, right? Now you finish with the first line, you get a semicolon to go to the next line while you're writing in matrix. Then you go 17, 18, and 35. Then you give another semicolon because you need a third row based on the table. Then you get 7, 10, and 24. X would be equal 4, 0, and 0. Then the next line would be 6 space 6, then space 0. Then you would be 0, 3 space 5. So the table was saying, so you got D1, D2, and D3 for the first cost table. And for the number of loads, you can see X is representing the number of loads. If we run the code, add to path, and you should be able to get the total to be, remember you have S1 and D1, D2, D3. So that's how the cost will be per factory and per load. And if you want per factory only, then you're going to take the sum of the total for your multiplication. And the total cost overall would be the sum of the total. I'm not a fan of saving things in your mind, but you know, if you have a cheat sheet on the side that you understand it and you can look it up fast, find what you want, that works as well. Now for creating matrices, we know that you can call a variable. In this case, we have A equal, when you open bracket, now you start to write E matrix. So you have 1, then you give it a space or a comma as we learned before, then 2. Whenever you want to go with a new line for the matrix, then you go with a semicolon and you continue. Not necessarily the last row to have a semicolon to identify it. It's identified as you move to the next row. And in this case, we have A equals, as you see, then X equals 5 and 6. Then we have A equal A semicolon X. So here we use the semicolon so that we indicate when to end the row as we're entering the matrix. And if you want, in this case, to add an extra row to A, you can just do that by A equals A semicolon X. Then that's going to add whatever values in X into your original matrix. We have X to equal 5 and 6. Now you would say A to equal A semicolon X. As you're doing this last statement, you say, hey, I gotta add whatever values in the array X. You could call it a matrix X as 5, 6, 0, 0, or you can call it an array of 5 and 6 for X. Then you just want to add the values within X into your original A. By doing that, hitting enter, you're going to have, originally you had 1, 2, 3, 4. Now you have 1, 2, 3, 4, and you added another row, which is 5 and 6. Now, while having the matrix A equal 1, 2, 3, 4, 5, and 6 in mind, we need to know that individual elements of a matrix can be referenced with 2 subscripts. Probably already know those subscripts are indicating the column number and the row number along the matrix. So the first for the row and the second would be the column. So when you say A, open parentheses, not a bracket, 3, 2, so that will bring back to you number 6. So you're telling him, bring me back in matrix A the number in row 3 and column 2. Let's do that together. If I say A 3, 2, 3 rows, I mean the third row, second column, that would give you 6. What if we said, you can play around with it, A 2 and 2. So in the second row, second column, that should give you 4. And you can say A 1, and what if we said something beyond our columns? What's going to happen? Like we have the first row and the fourth column, but we don't have fourth column. You think it's going to execute it, it's going to give you back 0, or it's going to give you an error. You get an error because it exceeds the array bounds, as he say. That means there is no such thing as the fourth column. Your matrix is only having 3 columns. Now, there's an alternative way, but it's less common. You can use single subscript. In this case, you can think of the matrix as being as one tall line of values. That is column by column. So if you can say A5 for the matrix that we see here, A, what's going to give you? It's going to give you the 5th element. So the first way, you call which row and which column. We love that. Third row, second column, I can count, I know which one I want. While if you say A5, you need to imagine the matrix as being as one line, like 1, 3, 5, it's going here, 1, 3, 5, then 2, 4, 6, as if it is a one continuous line. Then you're calling back the 5th component of that line. It's not a feasible way to call out your components in the matrix because there is some huge crazy matrices. It's hard to put them in line. So you would imagine that matrix to be A equal 1, 3, 5, 2, 4, and 6. So you count, okay, position 1, 2, 3, 4, 5. But it's not a feasible way. Stick with the way that's indicating which row and which column you're talking about, so that you'll be able to always, doesn't matter how big is the matrix, to pull the needed component precisely. But remember not to confuse between which is which, rows first or columns first. But when you are in the industry, you don't need to save anything in mind. You can always pull back and have your cheat sheet, or you have a certain Excel sheet probably that you have your notes on it. Now for the transpose, you already know when you have the matrix that you created, A, if you say A prime, that will give you the transpose of A. So you're gonna see, so that's how A is looking like. Now, if you do the transpose, you gotta have the columns to be rows and the rows to be columns. You just invert everything, basically. So if you have the statement A equals 1 to 3, semicolon, 4 to 6, then B would equal A prime. So he will go, A would be 1, 2, and 3, because he told him 1 to 3. Go another line, then he will say 4, 5, and 6. B is the transpose of A, or you can have here A prime. That will give you 1 and 4, instead of being a column, they're gonna be a row. 2 and 5, instead of being a column, they're gonna be a row. 3 and 6, instead of being a column, they're gonna be a row. You already know that, but it's good to touch base on it since we are in the chapter of matrices. Now, the importance of the column operator in our matrices. Again, we have this matrix, 3 columns and 3 rows. Now, the statement is saying A of 2 to 3, comma, 1 to 2. That will result of having 4 and 5 as the first row, 7 and 8 as the second row. Now, what if I say A of 3, comma, then we have a column? What's going to give us? That will give us 7, 8, 9. What happened here? So you have the matrix, 3 rows and 3 columns. Now, when you say A, open parentheses, 2 to 3, comma, 1 to 2, so that's going to give you this part of the matrix. So you're taking second and third row, and you're taking first and second column. Remember, it's following the same convention. So in the first time we said, if we have that matrix, then we said, if you want to call a certain number, you got to put the number of the row where that number is, then the number of the column. He said A of 2 to 3, those are the rows, and 1 to 2, those are the columns. So he said take the rows, second and third rows, and first and second columns. That's going to leave you with the numbers 4, 5, 7, 8. So the MATLAB will display for you 4, 5, 7, 8. What's going to happen if you do A equals third, so the third row, and he's not choosing any column, he's just going to give you the complete third row, which is 7, 8, and 9. So the column here is telling, I don't care which column it is. I don't care which column it is. I just need the third row. Give it to me. So what he did for you, he put for you 7, 8, and 9, which is the third row in our matrix as we see it here in MATLAB. Now what if we say A of 1 to 2, comma, 2 to 3 would equal 1s of 2. That's going to tell you for the rows 1 and 2 and columns 2 and 3, so those, whenever you see a value that's non-zero, give me back 1. Remember when we talk about logical operators? Here he switched it into a digital 1. So you can compare how it was here. It was the first column 1, 4, 7. We had this 1 from before, so don't confuse about it. But he said from 1 to 2, like the first 2 rows, and for the columns 2 and 3, so we're talking about these 4 numbers, 2, 3, 5, and 6. 1s of 2, this is a function MATLAB. Whenever he see any value that's non-zero, he's gonna tell you it's a 1. Otherwise, he's gonna keep it as a 0. So he converted all those numbers into 1s. I can't tell of any application out of my mind right now for that, but it's good to know. Now you need to know how to duplicate rows and columns, what we call it as tiling in MATLAB, and we will understand in a second why we call it as tiling. Now you have A to equal 1, 2, 3. How are you going to do that? You're going to say A equal, open bracket, 1, space 2, space 3, close bracket. Then the MATLAB going to show you 1, 2, 3 for A. Now RipMat, you can imagine as repeat matrix. That's the abbreviation RipMat. He open parentheses A, comma, 3, and 1. So what he did here, he said repeat A for 3 rows and 1 column. Then you got 1, 2, 3, 3 times basically. Why I'm saying 1 column while we have 3 columns, that's the exact reason why they said as tiling. It's like you are making tiles. I'm gonna show you what's the logic behind this naming. So we have A equals 1, 2, and 3. So we have rows are 1, don't be confused by that. So 1 rows, and we have column 1, column 2, column 3, right? Now you can imagine this as a tile. So imagine this is a tile. Now when you say RipMat, so repeat the matrix. I don't know if we can call this matrix. It's basically an array, but assume there is zeros here, so it becomes a matrix. Now RipMat A, so we're talking about A here, comma, for 3 rows and 1 column. So this indicate rows, this indicate columns. What MATLAB gave us as an output, so the answer was, he gave us 1, 2, 3, 3 times. But you would say, well, I had 1 row and 3 columns. Now you told him repeat the row 3 times and the column 1 time. But we had here 3 columns and 3 rows. Why is that? That's basically because MATLAB, in repeating the matrix, he's imagining that for duplicating rows and columns, he's imagining that as a tile. So it's like you're telling him duplicate this tile for 3 rows. Okay, this is 1 row, 2nd row, and 3rd row. So those are not in 3 columns in this case. Those are in 1 column as a tile. It's like the tile in your driveway. So he imagined them as tiles. So the 1, 2, 3 became in 1 bracket, which is a tile. That's why he called it 3 and 1. Now deleting rows and columns, that's an important topic. Now we use the column operator and the empty array so that we can delete the entire rows or columns. Now if you go with A, open parenthesis, column, comma, 2, what he's gonna do, then you close and you equal empty parentheses. That's important. The parentheses are part of the expression. Now what's gonna happen in this case? That's gonna delete the 2nd column of A. So if your A is looking like this, you should see A now equal 1 and 3. But if your A looking like this, then you should see 1s and 3s. It's important, guys, to try that. Let's do it together. Let's say A equals 1, 2, 3, semicolon, 4, 5, and 6, semicolon, 7, 8, and 9. That's our matrix. Now, if I want to delete the 2nd column, what I'm going to do, so you say A, open parentheses, then you get the colon sign, not the semicolon, then comma, so you're telling him delete. You can imagine colon as the word delete. Okay, then you tell him now which column do you want to delete? Then I would say the 2nd one, close, equal, empty parentheses. Now he imagine I'm going to delete the 2nd column. What I got here, I got 1, 4, 7 and 3, 6, 9. So you can see the 2nd column here is gone. 2, 5, 8 is gone. What if we say A, open parenthesis, column, comma, 1 for the A in its current form? What's going to happen? Column, comma, 1. So now he's looking at the new A of having 2 columns. Remember, He forgot about the old one. Now what he gonna do? He just kept you with 1, 4, and 7. Now I want to tell him, delete the first one. Then he left you with 3, 6, 9. So what's A now? To confirm, just hit A. You know what's your current A. Now that's how we delete a column. How to delete a row? Should be same concept. So you say A, open parentheses, like you choose whatever row you want, comma, then semicolon. Then column, not a semicolon. Then that's gonna delete your row. Let's recreate another matrix and do it together. A equals 1, 2. A equal. Okay, now if we want to delete the first row, comma, column, close, equal, empty parentheses, empty brackets. That deleted the first row and kept the second and the third, and so on. You guys get the idea. Now, if you write the statement, A, open parentheses 2, column 2, column 6, equals empty brackets, what that's gonna do for this guy, you can see he said 1, then he jumped to 7, then he jumped to 5, then he jumped to 3, then he jumped to 6, 9. What he did, so the missing numbers here are 2 and 4 and 8. So he's telling the MATLAB to delete certain numbers. What if we said A2, column 2, column 6? That's going to give you 4, 2, and 8. So you're telling MATLAB to go 2 with increment of 2 all the way to 6, like the location 6 in the matrix. That's going to give you 2, 4, and 8. When you said equal equal empty brackets, that's going to tell MATLAB delete those components. So when you put this statement, A, open parentheses, 2, column 6, he give you back 4, 2, 8. While when we said equal empty brackets, those 3 numbers disappeared. So you just told him to disappear or to delete those exact 3 numbers. Let's do it together. 6, close, equal, empty brackets. That's going to delete those numbers and show you the rest in one row. That's how you delete a certain number or a multiplication of number. You can choose to delete only odd numbers, only even numbers, numbers which divide by a certain other number, and so on. Now, of course, logical vectors can be used to manipulate any matrix that we need. So we can use them to extract a certain selection for rows and columns from matrix. So now we have A to be a 3 by 3 matrix as we defined all the way from 1 to 9. Now if you say A, open parenthesis, column, comma, logical, open parenthesis, open bracket, 1, 0, and 1, then you close that. That's going to give you rows 1, 3, 4, 6, 7, 9. What happened here? This is the A that we got. So from 1 all the way to 9. When you do that, so you're telling him in the first column, keep the values. For the first column, keep it. That's true. 1. Second column is 0, so you kill it. Third column, you keep it. So he kept 1, 4, 7, and he kept 3, 6, 9, and he killed the middle column. You guys see what happened here? So A column, so we're gonna adjust the matrix, you would tell him, or we're gonna delete some stuff, comma, then you got the logical 1, 0, 1, we know 1 is true, 0 is false, and 1 is true. Imagine the matrix as 3 columns. The second column is 0 in the logical, so that's gonna be deleted while keeping all the ones you marked as 1. Not the best way to handle matrices, honestly. Logical vectors, it's known, they always complicate your code. Whenever you use them carefully whenever you really can't use them another way. Otherwise, in the long run, when you have 3, 4 pages code, they just complicate stuff for you. Now you can do the same exact thing if you say A equal parentheses column, then comma 1 and 3. So you're telling him keep columns 1 and 3 and ignore column 2. So he's going to show you A with columns 1 and 3 only. Now, the elementary matrices, what are they? They are a group of functions that help you generate initial matrices which are pre-programmed in MATLAB. You can use help elmat to know more about those, but those functions, the famous ones are, you can say zeros, you can say ones, and you can say rand, which we used before to generate random numbers, but those will help you to generate certain matrices. You can generate matrices of ones, matrices of zeros, or matrices with random numbers. Now, usually you use a certain argument, like if you want to generate a matrix that's n by n rows and columns, or n by m rows and columns, then you can always use the ones and zeros. Now, as well, there's another function called EYE, which is I. That's supposed to be the letter I because it replicates the identity. Probably you saw that in your calculus or in your mathematics course. So you are telling him what is the identity of 3 in this case, and that's going to give you, the identity have diagonal ones and the rest are zeros. You can say the identity of 1, identity of 3, identity of 5, and so on. Now let's have an example about this identity function that we had that will construct a tridiagonal matrix as using the statements here. A would equal 2 multiplied by I of 5, so 2 number will be multiplied by the identity matrix of 5. Then you would say for A from 1 to 4, comma 2 to 5, that would equal A 1 to 4, 2 to 5 minus the identity of 4. And for A 2 to 5, 1 to 4 would equal 2 to 5 and 1 to 4 minus the identity of 4. That's going to give you this result. So you started with identity of 5, then you multiplied by 2, then you subtracted certain components of the identity of 5 from the identity of 4 matrix. Let's try to run it. For curiosity, if we said identity of 5 alone, what's he going to give us? You're going to get identity with ones in the diagonal positions, and the rest are 0. While what you did here, you multiplied the identity of 5 by 2, then you subtracted that from the identity of 4 for certain components on the right bottom hand side of the matrix. Specialized matrices, again, elementary matrices, specialized matrices, those are, I would say, that's what happened when the coder or the scientist who's building a tool is just playing around. They are not very useful. It's just a show for the muscles of MATLAB. Now you can use the function Pascal of n. That will generate for you a Pascal matrix of order n. That would give you a symmetric, positive, definite matrix, and with the entire made up from Pascal triangle, if you ever heard of that. So if you say Pascal of 4, that's going to give you the Pascal matrix of 4. We talked before about the magic of n. That's another function will give you a magic square. Then you have another functions as gallery, HADAMARD, Hankel, and so on. So you can try those, but again, I'm not going to ask you about these. Those are too much optional, and I don't feel they add any value for you to be a good coder in MATLAB, but it's good to know that they are there. Now, MATLAB functions with matrices. Now, when you have a trigonometric function that have a matrix argument, then the function will operate, as we know, on every element of the matrix. Many MATLAB functions would operate on matrices column by column. So we're going to know what's the difference between those. Now, if you say A equals matrix 1, 0, 1, then the second row is 1, 1, 0. The third row is 0, 0, 1. Now, if you say all of A, that's going to give you the answer of 0, 0, 1. So for each column of A, where all the elements are true or non-zero, they will return 1. Otherwise, it's going to be returning to you as a 0. So in this case, all function will return a logical vector, which would take the answer for the matrix argument, and if you want to see that twice, you can say all, open parentheses, all of A. That will return 0 for you. Again, that's optional function. I wouldn't ask you about it in the final if you're interested in the exam. The important stuff, how you manipulate matrices. Now, the function DIAG stands for diagonal. That extracts or creates a diagonal matrix. Flip LR will flip from left to right for the matrix. Flip UD will flip from top to bottom. And ROT90 rotates the matrix. And trail will extract the lower triangle part. As you can see here, trail Pascal of 4 would give you the result of this. You can compare with the original matrix of Pascal 4. Now to go with arrays as element by element operations, we talked about that before. I believe you guys are familiar with that. If you have a matrix 1, 2, 3, and the second row is 4, 5, 6, if you say A dot to the power of 2, what's going to happen here? Each component of the matrix will be to the power of 2. You can see the 1 stayed 1, the 2 is 4, the 3 is 9, and so on. Now, how to use 4 for matrices? Let's together create a matrix, which I believe you already have. A equals 1 all the way to 9, 3 rows, 3 column matrix. Now, for V equals A, he say display V prime and end. Now, what's going on here? Remember in your homework one time, you go through each component of the matrix as you are in a for loop. So for V equal A, we'll say for V equal 1, then for V equal 2, 3, 4, 5, 6, all the way to 9. Display V prime. He's going to display for you what is the inverse of that matrix or array as it's being called MATLAB. Okay? So that's our matrix. For V equals A, display V prime. Now if you run it, it's going to happen. So that's your original matrix. After you run it in the for loop, you got 1, 2, 3 as the first column instead of being the first row. Then you got 4, 5, 6 second column, 7, 8, 9 the third column. That's because you did the transpose of the V. Now when you're done with that, try V equals A prime, then display V. What's going to happen? So V equals the transpose of the matrix A. That's going to give you the first row to be in a column that's separate. Second row will be in a column that's separate. Third row will be in a column that's separate. So the textbook is saying for V equal A prime, display V prime. That's wrong. That should be display V so that you can see it the way you see it here. Just keep that in mind in case you're using the textbook as your main way of information. Okay, if you guys done with that. Now for the multi-dimensional arrays, we know that arrays will be one row and several columns, one column and several rows. I mean the rows would be zeros. MATLAB arrays can have more than 2 dimensions. So you can create A equals 1 to 2, semicolon 3 to 4. Then you can add, in this case, instead of 2-dimensional, you can add a third dimension to A by saying A open parentheses column, comma, 2 would equal 5 to 6, semicolon 7 to 8. And MATLAB will bring back to you for the first one would be 1, 2, 3, 4. What you added would be 5, 6, 7, 8. In this case, you can say it's a 3-dimensional array. Now, matrix operations, how to do multiplication, subtraction, division for the matrix. I hope you guys are familiar with matrix multiplication rules. So if you have A, go ahead, do that new MATLAB. A equal 1, 2, 3, 4. B equal 5, 6, 0, minus 1. And let's see what does C equal A multiplied by B would give you. So if we run this, Do you guys still remember how to do the multiplication? I gave you a little hint to the side just in case you forgot it. So to get the 19 here, what we did, 1 by 5 plus 2 by 7. That gave you 19. For 22, you get 1 by 6 plus 2 by 8. That gives you 22. Again, here you have, if you have this representation in your textbook as 1, 2, 3, 4 multiplied by 2 and 3, how are you going to do that in MATLAB? You say A equals 1, 2, semicolon, then 3, 4, close brackets. The B would be transpose of B. So B would equal open brackets 2, 3, transpose. That's going to give you 2 and 3 in this way. You can't do it without transpose. It's going to be a wrong number. But you got to do it as transpose. Then you say C equals A multiplied by B. So now you represent this kind of mathematical formation into the MATLAB language correctly. That's going to give you C to equal 8 and 18. For the matrix exponent, we talked about it before. If you have A equals 1, 2, 3, 4 as a matrix, A to the power of 2 would give you every component in your matrix to be in the form of A multiplied by A, because A squared is A multiplied by A. So you can either say the matrix A to the power of 2, give you this answer, or you can say A multiplied by A. Here recognize that it's one matrix multiplied by another matrix. In this case, you're not giving 1 to the power of 2 and 2 to the power of 2 and so on. It's like multiplying two matrices together in the same way we learned, as we can see in the board. Other matrix functions, determinant is DET. Eigenvalues, when you are studying about vibration and work in the industry with a lot of vibrations and powertrains, you will use MATLAB is your best friend to find your eigenvalues, and there's a lot of magic happening into eigenvalues. So I strongly support you whenever you have it in your physics or math class to learn more about eigenvalues and eigenvectors. I and V is the inverse, and for the orthogonal factorization, you get QR and all other stuff. Now, to solve a linear equation, a system of linear equations using matrices, now we're talking calculus or we're talking mathematics. When you have a system of linear equation this way, how are you going to solve it in matrix format, regardless of MATLAB? You create firstly a matrix for the coefficients of x, coefficient of y, coefficient of z. So x will be, coefficient will be first column, y coefficient second column, as you can see here, and z coefficient is the third column, which is -1, 2, and -1. You see what happened here? He created the coefficients into a matrix form. Then you put your variables in another matrix, x, y, and z, in this format exactly. And what does those equations equal? Should be in a third matrix, which is B in this case, to equal 10, 5, and -1. Now mathematically, you would say A multiplied by X, like matrix A multiplied by X would equal matrix B. And the solution for X in this case, which is X, Y, and Z, would be A inverse multiplied by B. That's not transpose, that's inverse. So I and V of that component. So let's go ahead together and learn that before we conclude here. So you can say A divided by B for X, or you can say A multiplied by inverse of B. Same concept. So you can say either A divided by B or A multiplied by inverse of B. Same concept. It's like B to the power of -1.